everyone, welcome to today's lesson. In this lesson, we will continue with Chapter 6 and explain the design of mechanical transmission systems Part 2. First, we will take the ball-screw nut pair transmission as an example for design explanation. The ball-screw nut pair, commonly referred to as the ball-screw pair, mainly functions to convert rotary motion into linear motion or linear motion into rotary motion. 1. Working principle and characteristics. The structure of the ball-screw pair is shown in the diagram, which consists of the nut, the screw, the raceway, and the return guide device. 1. When the screw rotates, the balls in the raceway rotate and roll along the raceway, thereby driving the nut, or screw, to move axially. 2. After rolling along the raceway for several turns, the balls are returned between the screw and the nut through the return guide device, forming a closed loop. The diagram shows the structural principle of the ball screw, with the main components as follows. 1. Nut. 2. Screw. 3. Raceway. 4. Return guide device. Summary of characteristics. Ball-screw pairs are commonly used in mechanical transmission systems for high precision and high efficiency conversion between linear and rotary motion, and have significant engineering application value. 2. Accuracy and main dimensional parameters. The accuracy grades of ball-screw pairs are divided into 8 levels: 0, 1, 2, 3, 4, 5, 7, and 10. Grade 0 is the highest accuracy, decreasing sequentially. The accuracy of the ball-screw pair is selected based on the positioning accuracy requirements of the machine tool. Generally, the allowable average travel variation of the ball screw accounts for 1/3 to 1/2 of the machine tool positioning error. 3. Structural types. Thread raceway normal cross-sectional shape. The normal cross-sectional shape and dimensions of the thread raceway are the most fundamental structural features of a ball-screw pair. The common types include single arc and double arc configurations, as shown in the figure. The angle alpha between the common normal at the contact point of the ball and the raceway and the axis of the screw is called the contact angle, generally 45 degrees. Classifications: single arc raceway and double arc raceway. Ball circulation method. According to whether the balls contact the screw surface during the entire circulation process, it can be classified as internal circulation or external circulation. Internal circulation can be fixed internal circulation, code G, floating external circulation, code F. External circulation can be helical groove type external circulation, code L. Tube type external circulation, code C. End cap type external circulation, code D. Axial clearance preload methods. Common types of axial clearance preload methods include 5 kinds: double nut thread preload, double nut pitch difference preload, double nut shim preload, spring type automatic adjustment preload, single nut variable load self preload. Selection of ball screw pairs. When selecting a ball screw pair, the following calculations and checks must be performed: strength calculation, stiffness check, stability check, and critical speed check. Key points of checks under different usage conditions. 1. For large torque transmission and high precision ball screws, check stiffness. 2. For slender ball screws under compression, check buckling stability. 3. For high speed and long span ball screws, check critical speed. 4. When the screw operating speed is below 100 rounds per min, no need to check critical speed. Strength calculation. Under normal conditions, the strength criterion for ball screw pairs is that the equivalent dynamic load, the maximum dynamic load during operation, should be less than the rated dynamic load of the selected ball screw pair. The equivalent dynamic load is calculated as the cube root of the working life multiplied by the average axial load and the operating condition coefficient, divided by the accuracy coefficient. Stiffness verification. When a ball screw operates under the combined effect of working load and torque, the deformation per lead is shown in the figure. For buckling stability verification, the actual load-bearing capacity is calculated as the product of the buckling support coefficient, the elastic modulus of the screw material, the moment of inertia of the screw's minor diameter section, and the square of pi, divided by the product of the buckling safety factor and the square of the screw thread length. The critical speed verification is shown in the figure. After completing the design of belt transmission, gear transmission, and ball screw, we now look at the motion transmission of the control system. A motion control system uses mechanical components to transmit motion from the actuator to the load. By selecting the appropriate motor and transmission mechanism, the load can complete the desired motion profile. Through the transmission mechanism, speed and torque can be adjusted to meet different working requirements. Inertia refers to the resistance of an object to angular acceleration around a rotating axis, which can be expressed as the product of mass and the square of the radius. Torque refers to the rotational force acting on a mechanical element, which can be expressed as the ratio of power to angular speed. In the diagram on the left, the motor and the load are directly coupled, which can be expressed as the product of the load inertia and the angular speed. In the diagram on the right, the motor is connected to the transmission mechanism, which allows for the conversion of torque and speed. According to the conversion formula in the diagram, the equivalent load inertia referred to the motor side equals the ratio of the load inertia to the square of the transmission ratio. In speed-changing components, gears or pulleys can both apply this relationship to convert the load to the motor side. For actual transmission mechanisms, due to friction and heat, there will be some power loss, so the load inertia referred to the motor equals. From the diagram on the left, the torque referred to the motor side equals the load torque divided by the transmission ratio. From the above, the total inertia of the transmission mechanism equals the sum of the motor's own inertia, the coupling inertia, and the load inertia referred to the motor. Each transmission mechanism has corresponding calculation formulas based on the diagram on the right. Next, let us take belt transmission as an example to calculate the load inertia and torque referred to the motor. A belt transmission mechanism consists of two pulleys and a belt. If only pulleys are considered, first calculate the transmission ratio as the angular speed of the input pulley divided by the angular speed of the load pulley, which is also equal to the radius of the load pulley divided by the radius of the input pulley. According to the transmission ratio, calculate the equivalent inertia on the input shaft, which equals the sum of the input pulley inertia, the load pulley inertia, and the coupling inertia of the load, as well as the inertia generated by an object with mass m, each calculated using the inertia formula as shown in the figure. The load torque equals the sum of all external torques acting on the load divided by the product of efficiency and transmission ratio, where the sum of external torques includes friction torque, gravity torque, and machining torque. When the load is connected through two identical pulleys and a belt, the rotary motion of the motor can also be converted into the linear motion of the load. This is a commonly used motion control method in low inertia, low load conditions. As shown in the figure, to calculate the transmission ratio, take the reciprocal of the pulley radius. The schematic diagram of linear motion belt drive is shown on the right. The equivalent inertia on the input shaft equals the sum of the two pulley inertias, the load inertia, and the coupling inertia of the load, as well as the inertia generated by an object with mass m. The calculation for load torque is the same as that for pulleys, as shown in the figure. In this lesson, we study the principle of ball screw pairs, accuracy classification and verification methods, and analyze the calculation of inertia and torque for transmission mechanisms. That concludes this lesson. Thank you for listening. See you next time.